chess, it's always been this like ultimate test for AI.
Yeah.
Right? Like if it can conquer this game of strategy and intuition, what can't it do?
Mm-hmm.
We've seen some, incredible chess engines over the years.
Yeah.
But today, we're diving into a whole new approach.
Okay.
Using something called a transformer model. Now, you usually hear about these in like language processing, right? It's like the tech behind those crazy human-like chatbots.
Mm-hmm.
But chess,
Yeah.
that's different. That's a whole new board game.
It really is. It is fascinating to see how they're taking these transformer models, these tools designed for language, and applying them to something seemingly totally unrelated.
Yeah.
And getting such remarkable results. This is research coming out of UC San Diego, led by Daniel Monroe and the Leela Chess Zero team. Yeah, so these are the folks behind Leela Chess Zero, which if you're into AI chess, you know.
Of course.
Yeah.
It was a big
deal. Big deal.
look up.
Yeah, so clearly they're onto something pretty pretty big here. But before we get ahead of ourselves, can you break down these transformer models for us?
Sure.
What's the magic behind them?
So imagine trying to understand a conversation, right?
Yeah.
You're not just processing individual words in isolation. You're paying attention to the context. You're looking at how they relate to each other.
Of course, yeah.
To really grasp the meaning.
It's all about, yeah.
And transformer models work in a very similar way.
They use this mechanism called attention to weigh the importance of different parts of the input data. And in this case, that data is the positions of chess pieces on the board.
So it's not just about seeing like where the pieces are, but understanding like the relationships, like this knight is threatening that pawn, that kind of thing.
Exactly. It's about understanding the dynamics of the board.
Okay.
And that's where this position encoding comes in.
Right.
Think of it like translating a piece of music for different instruments.
Okay.
The underlying melody, the information, is the same.
Right.
But the way it's represented changes depending on,
Right.
whether you're looking at it for piano or guitar or whatever.
Okay.
So the position encoding is basically translating that chessboard into a format that the AI can understand and work with.
Got it. So it's like finding the right language for the AI to interpret this chessboard.
Exactly.
And in this research, they didn't just stick to one encoding method, did they?
They did it.
They experimented, right?
Yeah. So they tested 3 different methods.
Okay.
The absolute method, which is kind of the most straightforward, is just telling the AI where each piece is on the board.
Okay.
They also looked at relative bias, which starts to incorporate some information about how those pieces relate to each other,
Okay.
but in a more limited way.
Right.
But the one that really kind of stole the show, I guess you could say, was the more nuanced approach developed by Shaw et al.
Okay.
This method digs much deeper into those relationships between the pieces.
So it's like instead of just seeing it as a snapshot, the AI is starting to see the board as this like dynamic network of interconnected pieces.
Exactly. And that's what allows it to develop, a more sophisticated grasp of the game, because it's not just about where the pieces are, but how they interact.
Yeah.
They call this model chessformer.
Chessformer.
Yeah.
I like it. I like it.
Catchy, right?
Yeah, it's catchy. So this chessformer, using the sophisticated position encoding, what were the results like? Was it able to like hold its own against other top chess AIs?
Oh, it did more than hold its own.
Yes.
They put it up against established chess engines like AlphaZero, which, again, big deal in the chess world.
Yeah.
And even another transformer-based model called GC270M. And what's remarkable is that chessformer achieved equal, if not better, performance.
Okay.
But here's the real kicker.
Okay.
It did it using significantly less processing power. We're talking 8 times fewer FLOPS than AlphaZero.
Wow.
And a mind-blowing 30 times fewer than GC270M.
It's like saying this little tiny electric scooter can outperform a gas-guzzling muscle car.
Right.
That's wild. But beyond just being this like lean, mean chess-playing machine, the paper also highlights something else pretty amazing about chessformer, wouldn't you say?
Yeah, definitely.
Like one thing that really caught my eye was how they describe its playing style as surprisingly human-like.
Yes.
Which, I mean, come on, it's got to be like the holy grail of AI development, right?
Yeah.
Creating machines that don't just crunch numbers, but they understand, they strategize the way that we do.
Right. It really is. It's like when they say human-like, they're not just talking about, making smart moves.
Right.
It's about recognizing those subtle strategic nuances making decisions based on like a true understanding of the game, not just, brute force calculation.
So it's not just evaluating like a million moves per second, but understanding the why behind a move.
Exactly.
That's so cool. But do they give any like specific examples in the paper of this human-like play?
They do.
Okay.
And it's these examples where it really, where chess farmers' abilities, really shine through.
Okay.
So one really interesting case is this Fortress game.
Okay.
From the 23rd Computer Chess Championship. And in this game, chess farmer, well, actually, a slightly earlier version of it, managed to hold a draw against Stockfish.
Hold on. Stockfish? Yeah. The one known for its, like, crazy deep search.
Yes.
It outmaneuvered Stockfish.
It did.
That's impressive.
By recognizing and exploiting this defensive position that Stockfish totally missed.
Wow. So it's almost like this positional awareness, this big picture understanding.
Exactly.
That even some of these, like, super powerful engines might miss.
Yeah. It's not just about like raw calculation.
Right.
It's about seeing
a whole board.
The patterns.
Yeah, that's wild. And it's not just defensive strategies either, right?
Right.
There's that other example, the trapped rook scenario, also from a computer chess championship.
Yeah.
Where chess former made this like subtle, almost unassuming move. Pushing this pawn that like several steps down the line would actually trap the opponent's rook.
It's crazy.
So it wasn't like an immediate checkmate, but it was this like strategic maneuver to set up for future advantage.
Yeah, like setting a trap.
That's wild. It's like it was thinking like several moves ahead.
It's true.
Anticipating the opponent's actions, like, whoa.
It really is a glimpse into that future where AI isn't just reacting, but it's actually strategizing with that level of foresight that we usually, attribute to us, to human players.
Right.
But then it gets even wilder.
Okay.
Because chess former can go beyond these individual games.
Okay.
And it can actually tap into like the collective wisdom of chess history. The paper talks about its ability to recreate these incredibly complex sequences of moves played by grandmasters.
Oh, wow.
Like the king walk.
Okay.
Which is this like series of precise maneuvers to get the king into this position for strategic advantage.
So it's not just playing chess. It's like learning from the greatest players of all time.
Yes.
Recognizing patterns and strategies that have, stood the test of time.
Exactly.
It's like it's almost developing its own chess intuition based on centuries of like human ingenuity.
That's a great way to put it. It's like this bridge between brute force calculation and something that really does resemble human understanding.
Right.
And that's where things get like really interesting, because if an AI can achieve this in a game as complex as chess, what are the implications for other fields?
Exactly. Like if it can play chess like this, what other challenges could it tackle? Could we see this kind of AI making waves in like economics, urban planning, maybe even something like climate modeling?
It's a tantalizing thought.
Right.
Imagine like AI that can analyze these complex systems, anticipate problems, maybe even propose solutions with an efficiency and a foresight that like surpasses even our best human efforts.
But we're talking about a future where AI isn't just this like tool for analysis, but it's a partner in problem solving.
Yeah.
Helping us navigate these really complex challenges with a level of insight and like ingenuity that we haven't seen before.
And it's not just about, crunching the numbers and giving us probabilities, but it's about understanding the why. It's about explaining those solutions in a way that that makes sense to us.
That clicks with our human intuition.
Exactly.
It's like we're almost seeing like a new kind of intelligence being born,
Yeah.
One that can like not just analyze the data, but really like understand what it means, strategize based on that, and then maybe even help us grasp those solutions in a way that makes sense to us.
And I think that's what's so exciting about this research, right? It's like this glimpse into a future where AI isn't just about, cold, hard calculations, but it's about understanding these complex systems. It's about thinking ahead, strategizing.
Right.
And we're already seeing, the impact of AI in all these fields, right? Like medicine, finance, transportation.
Right.
But imagine if we could take it to this next level.
Yeah.
Where it has this nuanced understanding, this strategic foresight.
It's like instead of just like crunching numbers, spitting out probabilities, it's almost like they could like anticipate problems before they even happen.
Yeah.
Develop like these truly innovative solutions, the kind that we haven't even thought of, and then help us actually wrap our heads around them.
Yeah.
Like in a way that...
It's about pushing those boundaries,
Right.
right? It's not just about playing the game. It's about, like, fundamentally changing how the game is played.
Exactly. And who knows, this could be, like, just the beginning.
Right.
If we can do this with chess, like,
Yeah.
the possibilities in other fields are just
Endless.
mind-blowing. So, to kind of, like, wrap things up for our listeners, today, we've taken a deep dive into this crazy world of AI chess.
Yeah.
Where this new player, Chessformer, has really, like, taken center stage.
It has, and I think what's so cool is, it's not just that it can play a good game of chess, it's how it plays.
Right.
It's that strategic thinking, the efficiency, and that almost human-like understanding.
Right, and that's all thanks to those, like, transformer models.
Those powerful transformer models.
It's this really powerful reminder that we are living in, like, this age of just, like, crazy technological advancement. And AI is, like, it's out here, and it's changing the world.
It's true.
So if you're interested in learning more, diving even deeper into this, definitely check out the full research paper by Daniel Monroe and the Leela Chess Zero team. Super fascinating read.
Yeah, it is.
And as always, like, keep exploring, keep questioning, and keep diving deep into all of this, ever-evolving world of knowledge.
It's an exciting time.
Until next time. Okay, so get this. AI is, like, really good at chess now.
Yeah.
Not just, like, good.
Yeah.
It's, like, scary good.
It's pretty wild.
Yeah, so we're talking about this new research paper. It came out just the other day, actually. Mastering Chess with the Transformer Model.
Right, September 20th.
Yeah, so new. It hasn't even been peer-reviewed yet.
That's fresh off the presses, hot off the presses.
Exactly. And, I think a lot of people hear chess AI and they think Deep Blue. Right, like that's the classic example.
Right, just brute force.
Yeah, just pure computational power, millions of calculations per second. But this is different.
Oh yeah, this is completely different. We're talking about a potential game changer here. This paper, it was authored by Daniel Monroe and the Leela Chess Zero team. And they're exploring how these transformer models, which are already like shaking things up in fields like language processing, are now being used to dominate the chessboard.
Okay, so I get chess engines, right. But transformers, that sounds like something straight out of a sci-fi movie. Break it down for me. What are these things, and why should I care that they're playing chess now?
Well, imagine an AI that learns not by brute force, like calculating every single possible move, but by understanding patterns and relationships, even strategy.
So less like a supercalculator and more like a super student of the game.
Exactly. See, traditional chess engines, they've relied on these massive search trees. Picture them trying to map out every single possible move and counter move. Effective, but computationally incredibly expensive.
Okay, so if the old way is like navigating a maze, what makes transformer models so different?
These models, they're all about efficiency. They use something called attention. It's like they can glance at a chessboard and immediately zero in on the most important pieces and threats.
So they're not wasting time on irrelevant calculations.
Yeah.
They're getting straight to the good stuff.
Precisely. And what's remarkable is they're achieving comparable, sometimes even better results than those older engines, but using far less computational power.
Wow, so less is more? AI edition. That's pretty wild. But the paper kept mentioning this thing called position encoding. It sounds like that's a key piece of the puzzle. What is it?
You got it. Think of it this way. You can't just show a chessboard to a transformer model and expect it to understand the game, right?
Right.
It needs a way to interpret the position of each piece, to grasp the strategic significance. That's where position encoding comes in.
So it's like teaching the AI the language of chess.
Exactly. The researchers experimented with different position encoding methods, and what they found was that the most effective ones allowed the model to understand not just where the pieces are, but also their potential influence on the board.
So are we saying we've given AI intuition?
In a way, yeah. The paper highlights that the best position encoding methods, they gave the transformer model a sort of strategic awareness, more akin to how a human grandmaster would approach the game.
Okay, that's both fascinating and a little unnerving.
Yeah.
But this isn't just theory, right? This AI is actually winning games.
Oh, absolutely. And not just winning, but playing in a way that's strikingly human-like at times. The paper discusses some fascinating game examples that demonstrate this. In one instance, the AI was in what looked like a losing position, but instead of, going down swinging, it managed to salvage a draw.
And to put that off.
By building a fortress, something human players, they excel at, but traditional engines, they often struggle with.
That's incredible. It's like the AI understood the concept of not just attacking, but also defending.
Exactly. And this wasn't just a fluke. The paper highlights another example, where the AI made a move that surprised even experienced chess analysts. It trapped its opponent's rook in a way that seemed counterintuitive at first.
Oh, wow.
But ultimately led to a winning advantage.
So we're not just talking about an AI that's good at chess by crunching numbers, but one that's actually starting to show real strategic understanding.
It really is something.
This is blowing my mind a little bit.
Yeah, it's a significant development. And what's even more exciting is that this research, it opens up a whole new world of possibilities for AI, beyond just playing games.
Okay, now you've got my attention. What kind of broader implications are we talking about here? So if an AI can learn the, intricate strategies of chess, what else could it potentially understand? This feels huge.
Right. Think about it. We've trained an AI to navigate the complexities of chess, a game with set rules, but almost infinite possibilities.
Yeah.
Now imagine applying this type of learning to other fields.
Okay, yeah. Now my mind is going to all those sci-fi scenarios. But seriously, what kind of real-world applications could this have?
Well, what about fields like medicine or finance, even art? Areas where intuition and pattern recognition are absolutely critical.
You're saying this chess-playing AI could hold the keys to breakthroughs in other fields?
It's not that far-fetched. This research suggests that AI might be on the verge of a massive leap forward, from brute force calculations to a more nuanced, almost intuitive way of problem solving.
It's like we're teaching AI to think less like a computer and more like us.
And that's a profound thought. This research challenges us to rethink the very definition of intelligence itself.
Whoa.
What does it mean for a machine to truly understand something?
It's a question with huge implications,
Yeah.
but also really exciting ones.
Right.
Okay, this paper was about chess, but it sounds like the researchers see this approach as having much wider applications.
Absolutely. They actually draw some interesting parallels to other fields where transformer models are being used, particularly natural language processing.
Like those super advanced chatbots everyone's talking about, the ones that sound almost human.
Exactly. And what's fascinating is that these seemingly different fields, language and chess, they share a surprising amount in common. They both involve pattern recognition, long-term planning, strategy.
That's a great point. We think of language as this uniquely human thing.
Right.
But maybe the way we use it isn't so different from how we approach other complex tasks.
Yeah.
Like playing chess.
Precisely. And that's what makes this research so groundbreaking. It suggests that the same AI models could be used to tackle an incredible range of problems. Understanding human language, mastering complex games, maybe even revolutionizing entire industries.
This is giving me a lot to process, but before we get ahead of ourselves, let's come back to this chess AI for a moment. The paper did mention that even with these advancements, there are still some limitations to this approach, right?
That's right. These transformer models are incredibly powerful, but they aren't perfect.
Right.
One thing the researchers pointed out is that these models can be quite data hungry. They need massive amounts of data to reach their full potential.
Which makes sense, even for a supercomputer. Learning to play chess at a grandmaster level is no small feat. Were there any other limitations?
Another interesting point they raised is that while these models are great at finding strong moves, they can sometimes struggle to explain why those moves are good.
So they're like those chess prodigies who can beat grandmasters, but can't articulate their thought process.
Yeah.
They just see the right move.
Exactly. And that lack of transparency, it can be a bit of a black box, making it harder to fully understand how the AI is making its decisions.
Which is a problem if we want to learn from these AI systems, right? It's like, okay, that was amazing, but how did you do that?
Precisely. And that's a fascinating area of ongoing research, trying to make these AI systems not just powerful, but explainable.
So it's not just about creating AI that can outperform us, but AI that we can understand and learn from, AI that can teach us.
Absolutely. And that brings us back to the broader significance of this paper. It's not just about chess, it's about the future of AI itself.
So we've covered a lot of ground here.
We have.
From the technical details of transformer models to the philosophical implications of, AI that seems to think like us.
Yeah.
What's the biggest takeaway for you, the one thing you hope listeners will walk away with from this deep dive?
For me, the most important point is that we're at this pivotal moment in the evolution of AI, right? We're moving beyond just brute force computing power and entering a new era, one where AI is learning to approach problems with a more, I don't know, a more human-like intuition.
It's like we're witnessing the birth of a new kind of intelligence.
It really is.
One that could, reshape our world in ways we're only just beginning to imagine.
And that's both exhilarating and a bit daunting, isn't it? To think that we might be on the cusp of creating something that could surpass our own abilities in ways we never thought possible.
It definitely makes you think about the future.
Yeah.
About, the possibilities and the potential pitfalls.
Of course.
But if an AI can learn to strategize and outmaneuver us on a chessboard, what other amazing feats might it be capable of accomplishing?
The possibilities are truly mind-boggling. This research, it opens up so many doors, raises so many profound questions.
Yeah.
About the nature of intelligence, the future of work, even the very essence of what it means to be human.
It's a lot to wrap our heads around. But that's what makes these deep dives so fascinating, right? They challenge our assumptions, they expand our understanding of the world, and they leave us with a sense of wonder about what the future holds.
Well said. And I think sometimes the most important discoveries aren't just about finding answers, but about asking the right questions. Questions that push us to explore new frontiers of knowledge and possibility.
Absolutely. Well, folks, there you have it. Another deep dive completed.
Another one.
Another layer of understanding unlocked. Until next time, stay curious.
Imagine an AI that doesn't just play chess, but it understands it, Like a grandmaster, seeing the board with almost human intuition. That's what we're diving into today.
Yeah, it's a really fascinating area of research, pushing the boundaries of what we thought AI could do.
Right, and for the longest time, it felt like chess AI was all about brute computational force, just crunching numbers faster and harder than any human ever could.
Yeah.
But this paper, Mastering Chess with the Transformer Model by Daniel Monroe, suggests a whole new approach. He's part of the Leela Chess Zero team, or LC0 for those in the know, which is already a powerhouse in the chess AI world.
Yeah, LC0s have been pushing the boundaries of what's possible with AI and chess, and this new research is definitely turning heads.
Okay, so before we get into the specifics of this chess former and how it's shaking things up, can you give us a quick recap of how we even got here, like Chess AI 101?
Absolutely. So early chess engines were all about brute force, using algorithms to create these huge trees of possible moves, and then evaluating those moves based on, pre-programmed rules.
Right.
Think of it like, if I move my pawn here, what are the chances it becomes a tasty snack for my opponent?
So it's very strategic, but also kind of robotic.
Exactly. But then came a major shift with DeepMind's AlphaZero. It used deep neural networks and a method called Monte Carlo tree search, allowing it to actually learn from its own games. It was a game changer, quite literally, and ended up being significantly stronger than even the best human players.
And that's where LC0 comes in, building on those AlphaZero foundations, but always looking for those new innovations.
You got it. And that leads us to this paper and the world of transformers.
Now transformers are having a moment in the AI world, right? They're not just for giant robots anymore. What makes them so special?
That's a great question. What's fascinating about transformers is their ability to understand relationships and patterns, much like how we process language. It's not just about seeing individual words, but understanding the context and the connections between them.
So instead of just seeing pawn, knight, bishop, a transformer can grasp the strategic relationship between those pieces on the board.
Precisely. And this paper takes that incredible pattern recognition power and applies it to chess, asking, can we use this to master the game in a whole new way?
And spoiler alert, the answer is a resounding yes. But we're getting ahead of ourselves. Before we dive into those mind-blowing results, let's unpack how this chess former actually works. All right, so let's get our hands dirty here. This chess former, it's not just any old transformer model playing chess, is it? There's something special under the hood, right?
You're absolutely right. What's remarkable about the chess former is its efficiency. Monroe and his team managed to create an architecture that's simpler and requires less computational power than previous models.
Okay.
Yet it achieves remarkable results.
Hold on, back up a second. Less computational power, better results. That's like saying my old clunky chess computer could suddenly outplay Magnus Carlsen. How'd they pull that off?
It all comes down to a clever technique called position encoding. Imagine trying to explain a chessboard to someone who's never seen one. You wouldn't just list the pieces right.
Right.
You describe their positions and their relationships to each other. That's what position encoding does for the chess former. It teaches it to see the board in a more human-like way.
So instead of processing a jumble of pieces, it understands the strategic layout, almost like visualizing the lines of attack and defense.
You got it. And the paper explores a few different types of position encoding to find the most effective one. What they found is that this encoding is absolutely crucial. It's like giving the AI the right lens to understand the game's deeper language.
So they've essentially given this chess former a crash course in chess strategy just by tweaking how it sees the board. That's wild. But enough about the theory. Let's get to the fun part. How does it actually stack up against, the big dogs of the chess AI world? Hold on to your hats, because this is where it gets really exciting. We've got this lean, mean chess former that sees the board like a human grandmaster. How does it actually perform? Like, how does it stack up against the top chess AIs out there, the ones that have been around?
Well, let's just say it didn't just compete, it dominated.
Oh, wow.
And here's the kicker. It wasn't winning through brute force calculation like some chess engines. It was all about strategy, recognizing subtle positional advantages in a way that, honestly, really impressed even seasoned chess experts.
So it wasn't just like, I can see 3 moves ahead, 4 moves ahead, 5 moves ahead. It was like, no, I understand this like a person.
Exactly, yeah.
Wow. Are there any specific examples from the paper that really highlight this?
Absolutely. So in one game, the chess former used a fortress defense that completely baffled Stockfish.
Oh, yeah.
Which is one of the, the most powerful chess engines out there.
Right.
And to be fair to Stockfish, it's a strategy that relies on long-term positional understanding, not just calculating a few moves ahead.
Oh, wow. Even I wouldn't have seen that coming, and I've been playing chess since I was a kid. Okay, hold on. What does all this mean? Like, it's cool that this AI can play chess like a human, but is there, like, a bigger takeaway here for our listeners?
That's the million-dollar question, isn't it?
Yeah.
What's truly fascinating here is that this goes way beyond just a game.
Okay. These results have big implications for the future of AI. For one, it shows the power of tailoring AI to specific tasks, rather than relying on a one-size-fits-all approach.
So, like, instead of trying to build a general-purpose AI that can kind of do everything okay, we focus on building specialized AIs that can do one thing really, really well.
Precisely. Think about AlphaFold, which is revolutionizing how we understand and design proteins. That's a great example of domain-specific AI. But there's an even bigger picture here, this idea that AI can move beyond brute force and start exhibiting more nuanced human-like understanding that's groundbreaking. If we can teach AI to really think strategically in chess, what other complex problems could we apply this to?
Oh man, my mind is officially blown. Transformers, position encoding, AI that gets it. It's a lot to process, but in a good way.
Yeah.
So if our listener is walking away from this deep dive with one big takeaway, one thing to ponder on their next walk, what would it be?
I'd say this. If AI can learn to approach complex problems with the strategic insight of a grandmaster, just think about the potential we're unlocking. From tackling climate change to developing new medical treatments, the possibilities are, they're truly exciting.
Absolutely. And on that note, we'll wrap up this deep dive into the world of chess and AI. Until next time, keep learning, keep exploring, and keep asking, what if?
All right, folks, ready to dive into some seriously cool chess AI stuff?
Absolutely.
Today, we're looking at a paper that could totally change how we think about computers playing chess.
Oh, yeah.
Yeah, like moving away from just brute force calculations and towards something almost like human intuition.
That's a fascinating idea.
Isn't it? And the best part is, this isn't some sci-fi dream. This is happening now.
Wow.
Hot off the press research from UC San Diego. And get this, they're working with the team behind Leela Chess Zero.
LC0, right, the open source chess engine.
That's the one. Their paper's called Mastering Chess with the Transformer Model, and, well, I gotta admit, Transformers kind of blew my mind when they started showing up in those crazy realistic chatbots.
Yeah.
But chess, how do you even begin to teach a computer to get chess?
Yeah. It's a really interesting question, and to understand how big of a deal this is, it helps to know how chess AI has worked, well, traditionally. Imagine, like, this massive decision tree inside the computer's brain.
Okay, so it's trying to map out every single possible move.
Exactly. It's called a tree search algorithm, and it's been the backbone of chess AI for a long time. And to help the AI make sense of all those possibilities, they use these things called evaluation functions. Think of them like a set of rules programmed into the AI, almost like having a chess master whispering in its ear, good move, bad move.
So like a knight on that square, 2 thumbs up.
Precisely. A pawn chain like this. Very strong. It's all very structured, very calculated.
Which makes sense, I guess. But it's also kind of dot limited. I mean, chess isn't just about calculating every possible move, right? There's this whole other level, that human element of intuition, of strategy, those aha moments that you see with grandmasters.
You're absolutely right, and that's what's been missing from these traditional engines. They can calculate like nobody's business, but they lack that certain something. That's where this new research, these transformers, come into play. Instead of brute force, they're all about recognizing patterns, relationships, kind of like how a human player learns to recognize a classic pawn structure and instantly gets a feel for the board.
So less about crunching numbers and more about understanding the soul of the game.
You could say that, yes. And that's what makes it so exciting. It has the potential to unlock a whole new level of play, and not just for the elite few. Now, to be fair, engines like AlphaZero and LC0, they've already started using neural networks and this other cool technique called Monte Carlo tree search, MCTS for short.
MCTS. That sounds intriguing. Tell me more.
Okay, so instead of methodically evaluating every single possible move, imagine the AI playing out thousands of simulated games in its head, just trying out random moves to see what sticks. That's the essence of MCTS, and it's a total game changer.
So it's like the AI is playing ski chess against itself to figure out the best moves.
In a way, yes. But even with all that, traditional AI is still limited by its reliance on brute force. This new research, though, suggests that transformers could be way more efficient. We're talking about reaching even higher levels of play, but using a fraction of the computing power.
Now hold on. Less power, but potentially stronger play. How does that even work?
It all comes down to something the researchers call position encoding, basically. Giving the transformer the tools to understand not just where the pieces are on the board, but what those positions actually mean.
Okay, now you've got my attention. Position encoding. Sounds like we're going deep. Position encoding. It's like instead of just seeing pieces on a board, the AI starts to understand the strategy, right?
Exactly. It's like, imagine trying to explain a brilliant chess move, like sacrificing your queen to someone who's never played before. They'd be like, you're giving up your most powerful piece? Are you nuts?
Yeah, they're just not seeing the bigger picture.
Exactly. They don't see the strategy, the long game. Traditional AI, in a way, it's been a bit like that. Good at calculating, but not so good at understanding the meaning behind the moves.
So how do you give an AI that deeper understanding? How do you teach it to see the board like a grandmaster?
That's where position encoding comes in. It gives the transformer a way to actually understand the relationships between the pieces, the strategic implications of every move.
So instead of just seeing a pawn on d-Fi, it understands how that pawn influences the entire board.
Yeah, exactly. It's like it starts to see the web of relationships, the interconnectedness of everything.
Wow. Yeah. So it's not just knowing where the pieces are, it's understanding what their positions mean.
Precisely. And the really cool thing is we're not even programming in specific rules about strategy. The transformer learns all this from the data itself.
So you're saying it's developing its own chess intuition just by analyzing thousands of games?
Exactly. Now, you mentioned earlier that the researchers tested a few different methods for this position encoding, right?
Right. They had 3, if I remember correctly.
Yeah. They started with a simple approach. Absolute position embeddings. Basically, each square on the board gets a fixed value, a sort of identifier.
Okay, so the AI knows where everything is, but it doesn't get the strategic importance of each location.
Yeah, like having a map with all the street names, but no sense of which neighborhoods are cool,
Right, right. So what was next?
So to make it a bit more sophisticated, they moved on to relative position embeddings. This time, it wasn't just about individual squares, but about the distances and relationships between pieces, like this knight is 2 squares away from that pawn, or that bishop is threatening my queen.
Okay, so the AI is starting to see the connections, the potential threats. But it still seems a bit basic, right? Like, what about all those subtle strategic nuances we talked about?
Exactly, and that's where their third method comes in. This one's called Shaw et al. Encoding, and it uses these things called learnable vectors.
Learnable vectors. Okay, now you're just using fancy words to sound smart. Broke it down for me.
All right, think of it like this. Each piece gets its own little bundle of information, a vector, that captures its strategic value in that specific position.
Okay, so what kind of information are we talking about here?
Well, it could be anything from the piece's attack potential to its defensive strength, how well protected it is, its relationship to key squares on the board. So instead of just seeing a pawn on d5, it understands that this particular pawn is, say, part of a strong pawn chain, but also vulnerable to attack, and 2 squares away from promoting to a queen.
Wow. Okay, now that's impressive. It really is like the AI is developing a feel for the game.
Exactly. And the crazy thing is, this Shaw et al. Encoding wasn't just a cool idea on paper, it actually worked incredibly well in their tests.
So they actually built chess AIs, like full-on AI players,
Yeah.
using these different encoding methods. Did they give them cool names or something?
They did. Well, sort of. They called them agents, and they actually pitted them against some of the biggest names in chess AI.
No way. Are you serious? Like Stockfish. Did they go up against Stockfish?
Even better, they tested them against AlphaZero.
You're kidding.
Yeah.
AlphaZero. The AlphaZero. Okay, I gotta know. How did these, what did you call them, agents, stack up against the champ?
Well, their smaller model, which they called, get this CF6M policy, it went head-to-head with AlphaZero, and, well, you're not going to believe this.
Tell me.
It actually beat AlphaZero.
No way, seriously.
Yeah, not only did it achieve a higher ELO rating, like a really impressive 3,300 ELO compared to AlphaZero's 3,200, but get this, it did it using way less processing power.
How much less are we talking?
8 times less. It was using 8 times less computing power than AlphaZero, and it still won. It's incredible.
8 times. That's insane. It's like bringing a knife to a gunfight and still winning.
Yeah.
What about their larger model? How'd that one do?
Their larger model, CF240M policy, it achieved grandmaster level play, which is amazing in itself. But what's really interesting is that it actually matched the puzzle-solving accuracy of a much larger, more computationally expensive model from earlier research, GC270M.
So not only are these new AIs crazy strong, but they're also super efficient. This feels like a total game changer, not just for chess AI, but for AI in general.
I think you're right. Imagine what we could do if we could achieve these kinds of results with less computing power in all sorts of fields. It could make AI so much more accessible, more widely used.
Right. It's like the difference between needing a giant supercomputer and just using your phone. This could really open things up.
Absolutely. And I think this research really highlights the importance of, designing AI that actually understands the problem it's trying to solve.
Yeah.
It's not just about brute force anymore. It's about finding those clever domain-specific solutions.
It's like teaching a computer to not just play chess, but to actually appreciate the game, the strategy, the art of it all. And who knows, maybe someday soon, we'll all have our own personal chess grandmasters powered by AI right in our pockets, ready to challenge us to a game anytime, anywhere. If you're as fascinated by this stuff as we are, I highly recommend checking out LC0, the open source engine that's pushing the boundaries of chess AI. And hey, maybe you'll even discover your own inner chess prodigy along the way.
Until next time, happy learning, folks. Chess, right. It's always been this ultimate test of strategy and, thinking ahead. But when AI stepped onto the board, things got really, really interesting. I mean, think about Deep Blue going up against Kasparov, back in '97. It kind of felt like this epic showdown between, human brains and computational power.
Oh, absolutely. And for a long time, that was basically the game plan for chess AI, just pure brute force calculation, evaluating millions of moves every second just to find that, the optimal path to checkmate.
It's like they created a supercomputer that could play speed chess with it.
Exactly.
But the research we're diving into today, it suggests that there's this whole other way that AI can approach the game. We're talking about a new breed of chess AI, one that plays less like a machine and more like a grandmaster.
Yeah. And what's really intriguing about this paper, and you have some excerpts in the source materials there, is that it zeroes in on this thing called a transformer model. Right.
Yeah.
See, traditional chess engines, they were all about crunching numbers, evaluating each possible move based on, its immediate tactical value.
Okay, so help us understand what makes a transformer model different. How does it change the game, so to speak?
Right. Well, imagine how a human grandmaster would size up a chessboard. They wouldn't go through every single square with the same intensity, right? No, they'd zero in on the key areas, like the hot spots where the real action's about to go down.
Our brains, we instinctively know how to prioritize information, right? Focusing on what's most relevant at that exact moment.
Exactly. And that right there is the essence of a transformer model. It uses this mechanism called attention, which lets the AI do something remarkably similar. So instead of just, blindly calculating all the possibilities, it learns to identify and prioritize the most critical parts of the board, much like a human player would.
So it's not just about raw processing power anymore. It's about learning to actually see the board strategically, recognizing patterns and relationships that a traditional engine, well, might completely miss.
That's the key difference. This research focuses on a specific transformer model called, get this, chess former. And one of the things that makes it so effective is how it uses position encodings.
Okay, now let's unpack that a bit. What exactly are position encodings, and how do they contribute to this more human-like understanding of chess?
All right, so think of it this way. If you're trying to make sense of a sentence in a completely foreign language, you wouldn't just look at the individual words in isolation, would you?
No.
You'd need the grammar, the syntax, how those words all fit together to actually make meaning.
So you're saying that in chess, each piece is like a word, and how they're arranged on the board, their relationship to one another, that's like the grammar of the game.
You got it. These position encodings, they're basically mathematical representations of that grammar. They teach the AI how to interpret the board, how to understand what each piece's placement really means in the larger context of the game.
Fascinating. So it's not enough to know how each piece moves by itself, right?
Yeah.
It needs to understand how their positions create threats, offer opportunities, influence the entire flow of the game, all of it.
Exactly. And what's really remarkable is that ChessFormer, it doesn't rely on any pre-programmed chess knowledge. The researchers just fed it this massive data set of games and let it learn these patterns and relationships all on its own.
So it's like it learns to speak chess fluently just by immersing itself in all those games. Kind of like how we develop intuition, wouldn't you say?
That's a great way to put it. And, the paper actually highlights some pretty compelling examples of this intuition in action. Like, there's one scenario where ChessFormer, it manages to salvage a draw from a position that, honestly, most players would consider a lost cause.
The classic comeback story, always a fan favorite. So how does it pull that off? What's the secret sauce?
Well, in this particular game, what ChessFormer does is it recognizes the potential to build this impenetrable fortress. That's what we call it in chess, a defensive formation that's incredibly tough to break down, even if your opponent has more pieces on the board.
So it's not just about counting up the pieces anymore. It understands these more, these higher level concepts like positional advantage and thinking many moves ahead.
Exactly. And here's the thing. Even Stockfish, which is this really powerful, traditional chess engine, they threw billions of calculations at the same position, and it still thought the other side had a clear advantage. It just completely missed those defensive possibilities that ChessFormer was able to spot.
Wow, that's wild. So it's almost like ChessFormer has this deeper understanding. It can see these subtle patterns and possibilities that the traditional engines just miss entirely. Did the researchers find any other examples of this kind of strategic depth?
Oh yeah, there are a bunch. In another example, ChessFormer shows that it gets this classic chess tactic, trapping your opponent's pieces. So we're talking middle game here. And it makes this series of moves that at first glance they seem kind of subtle, but ultimately they box in the opponent's rook. Makes it practically useless.
That's amazing. Especially because, the researchers didn't program that tactic into it beforehand, right?
Yeah.
It learned it all from just playing.
Exactly. And to really put it to the test, they actually tweaked this scenario a bit. They made this tiny change to the board, just enough to make that trapping maneuver impossible.
Oh, so they threw a wrench in the works, see if it could adapt. Did ChessFormer fall for it?
Nope, not at all, actually. It instantly recognized that the situation had changed. And just like that, it completely shifted its strategy. It's like he understood that the old plan wouldn't work anymore and just seamlessly adapted on the fly. That's what's so impressive, this adaptability, this ability to think flexibly. That's what separates the good players from the truly great.
It's like ChessFormer isn't just playing chess. It's like it's actually thinking about the game in a way that, honestly, we've never really seen from AI before.
You're right. This research is definitely pointing to a whole new level of sophistication, especially when it comes to AI grasping these really complex games. And it's not just about tactical awareness either. The researchers also found that ChessFormer could actually recognize and execute long-term strategic plans.
So not just winning the battle, but winning the entire war. Give us an example. What kind of long-term planning are we talking about?
So get this. In one game, ChessFormer actually identifies and plays out this famous, like, king walk sequence from a
Yeah.
real Grandmaster game. And I'm not talking about some flashy three-move combo. This is a plan that spans multiple moves where you need a really deep understanding of how all the pieces work together, positional advantage, and how to maneuver your king to safety, all while you're squeezing your opponent.
Wow, it's like it can see the whole board, not just how it is now, but how it's going to evolve, like anticipating the opponent's moves and planning steps ahead. That's incredible. But I'm curious, with all this talk about how amazing Pressformer is, did the researchers find any weaknesses? Anything it struggled with?
Well, it's important to remember that this is still the cutting edge, right? ChessFormer isn't perfect by any means. Like, even though it shows this impressive strategic depth, it hasn't totally abandoned those brute force calculations from the old school chess engines.
It's still crunching a ton of numbers, just, well, maybe with a bit more finesse than those earlier engines.
Yeah, exactly. It's not about throwing those old search algorithms out the window. It's more like giving them an upgrade, combining that raw power with like a layer of strategic intuition on top.
So it's like a grandmaster who also happens to have a supercomputer in their brain, right? It's the combination of both that really makes them unstoppable.
Precisely. Yeah. That's what I find so exciting about all of this. This research is hinting that maybe the future of AI, like at least when it comes to these really complex domains like chess, it might not be about just building faster and faster computers. It might be about figuring out these like more elegant ways to, to blend those brute force methods with something that, well, that actually resembles human understanding.
Okay, so we've really gone deep on how Chessformer works, how it can like mimic our intuition and strategic thinking. But let's zoom out for a second.
Yeah.
What does this all mean, the bigger picture, especially for our listeners out there who are fascinated by the world of AI? What's the takeaway?
That's the big question, right? I think for me, one of the biggest lessons here is that like domain-specific expertise, it really matters in AI development.
Yeah.
And we're seeing this in a ton of different fields, actually, from protein folding to even drug discovery. We're finding that AI models that are specifically designed for a particular task, they're starting to outperform these like more general purpose AI models.
So it's not about building this one, super AI to rule them all. It's recognizing that even in AI, expertise comes from specialization.
Absolutely. And I think ChessFormer is like this really powerful example of that.
Yeah.
By combining how versatile transformer models are with these really well-designed position encodings that, really capture the essence of chess, they've created an AI that not only kicks butt at the game, but it also does it in a way that feels honestly remarkably human.
It really makes you think, if we can reach this level of sophistication in a game as complex as chess, what other problems could we be solving with this approach? What other fields could benefit from this kind of specialized AI?
Oh, the possibilities are huge. Just imagine AI systems that can help doctors diagnose illnesses, not by just looking at symptoms, but by actually understanding, the underlying mechanisms of the disease. Or AI-powered tools that can tackle like climate change, not just by crunching numbers, but by actually coming up with truly new, innovative, and sustainable solutions.
It's like we're on the verge of a completely new era for AI, where machines aren't just solving problems, they're actually understanding them at a much deeper level.
Exactly. And as we keep developing these increasingly powerful AI systems, it's more important than ever that we do it responsibly, making sure that, they're aligned with our values and that we're using them to make the world a better place. But hey, that's a conversation for another deep dive, don't you think?
Absolutely. A huge thank you to our expert for taking us on this incredible journey through the world of AI and chess. And to our listeners, we hope this has sparked your curiosity and maybe inspired you to explore these topics even further. Until next time, keep those minds engaged.